Hello everyone. Today this is the bonus challenge of gimbal locking and quaterions. And here in this text we want to explain why there is a gimbal locking in if we use the Euler angle to define the rotation, while there will not exist the gimbal locking where we define the rotation of quaterions. And first of all, we want to show the rotation matrix of Euler angle, which is one is alpha, which is rotating x axis, and beta, which is rotating y axis, and gamma rotating z axis. And this is the general way we use Euler angle to define rotation. And there's an interesting fact that if we insert pi divided by 2 or 1.5 dot pi, we will see that we have the result matrix right here, which can see the alpha and gamma is being coupled. So if we even though we can't really tell which one is alpha and gamma, which means that and one remain constant, so which means that no matter what we change x and z, it will only remain the rotation on the same plane. And I've written a Python code to show the gimbal locking. And here I have imported the numpy, scipy, the scipy rotation, and matplotlib. And here we want to show that first of all, if we insert 0, from the for the initial condition, and the other is just animation code. And here's if we update all the frame, and to see here, we will see the rotation will be the normal rotation, because we have update the theta, the degree, and the axis will be rotated if we're in a normal case. But if initial condition change to 90, which means pi divided by 2, and the y-axis is remain constant, above it have been remain constant, and we'll see the z-axis has been changed to the x direction, and while others 2 axes will only change remain on the same plane, which we can see from the above. Yep, the 2 axes are only changing, rotating from the same plane. So we can see this is so-called the gimbal locking, which if we use the pi divided by 2 to the rotating angle to y-axis, no matter what angle we choose from the x and z, they will always stay in one plane, which means at first it will be 3 degrees of freedom, but if we change to y to pi divided by 2, and the degrees of freedom will be decreased to 2. And we can check this by if we change the x and the y and z axis from the initial condition. So here is the z, here's now y, here's z, and here is y. And the axis will continue to start rotating, which will not cause the gimbal locking. So this is a gimbal locking. And we want to show that what is quaterions. So quaterions is a new way to define rotation, which have 4 components, and Q0 is the real part, and Q1, Q2, Q3 is the imaginary part. And the relation between the Euler angle and quaterion is common below. So we have this relation of transformation of Euler angle and quaterions. We can see if we given a position of the vector we want to use, and the alpha, beta, gamma, of the rotating angles, and if we set the vector to 0 x y z, and use the and p plane is the q multiply p and q inverse, which q inverse is the q0 minus q1 minus q2 and q minus q3, and the q plane of the x plane, y plane, z plane is what we really want when we rotate an angle defined by alpha, beta, gamma. And what's the reason? The reason is that quaterions can overcome the Gimbal lock is they can represent the transformation from the initial coordinate frame to the body fixed frame in a single rotation, and that's the reason, because it just depend on one single rotation. And yes, so I've also written a animation for quaterions and Euler angle, the rotation of it, and we'll see. Well, the Euler angle remain, the other two axes remain on one plane, but the Euler angle stays 3 degrees of freedom, while others are 2. So this is my bonus challenge.